So, good afternoon, everyone, and welcome back to the next session on computer networks. So, we'll just, before we go for this lesson today, we'll just recap what is that we have studied in the last class. So, in the last class, we have looked into the layering model here. So, these are the various 7 layers that are being present in OSI reference model: the physical layer, data link layer, network layer, transport layer, session layer, presentation layer, and the application layer. So the physical layer is responsible for transmitting the bits over the medium to provide mechanical and electrical specifications, and the data link layer is responsible to deliver the frame from one hop to the other hop. Between 2 adjacent nodes, the data will be delivered by making use of this data link layer. And the network layer is responsible for moving the packets from the source to the destination. So it is at this network layer you are going to route the packet from the source to the destination, and actual data transmission, end-to-end transmission, that is from a process at the sender's end to the receiver's end, will be done at the transport layer. So the network layer delivers the packet from the source to the destination, and the transport layer delivers the packet from the sending process to the receiving process. So this is actually the end-to-end transmission that takes place at the transport layer. And above the transport layer is the session layer, which is responsible for establishing a session, managing and terminating the session. It is at this layer you are going to have the dial-up control in our session, and also it is responsible for synchronization. And the presentation layer is responsible for data translation, that is data representations and on different systems will be converted into our canonical form at this particular layer, the presentation layer. And it also offers compression of the data so that it takes less space when it is being transmitted over the network, and also it offers as security in the form of encryption here at the presentation layer. And at the application layer, it allows the end users to access the network resources by the application layer in the form of various applications that are being provided to the end user. So these are the 7 layers that we have in the OSI reference model. So when you go for the differences between the TCP/IP and the OSI reference model, so these 2 layers, session layer and the presentation layer, which we have here, is offering minimal services, and hence they are being merged into a single layer at the and the application layer when you go for TCP/IP reference model. And when you go for this layers in the TCP/IP reference model, so these 3 form a single layer, that is the application layer. We have a transport layer, we have network layer also, and these 2, in most of the literature, these 2 are being combined when you go for TCP/IP reference model, which we call it as a host to network layer here. So these are the various layers that we have in the TCP/IP reference model. Apart from this number of layers differences that we have in the TCP/IP and the OSI reference model, there's a difference even at the transport services that are rendered at the transport and network layers also. So when you go for OSI reference model at the transport layer, it offers only connection-oriented service. But whereas when you go for TCP/IP reference model, it offers us both connection-oriented as well as a connectionless service at the transport layer. So in the form of TCP, it offers us a connection-oriented service, and in the form of UDP, TCP/IP offers a connectionless service at the transport layer. And at the network layer, when you go for OSI reference model, it offers us both the connection-oriented as well as a connectionless service. But whereas when you go for TCP/IP reference model, only connectionless service is being offered at the network layer in the form of IP protocol here. So these are the differences that we have between OSI reference model and the TCP/IP reference model. So this is what we have seen in the last class. So now we'll jump on to the next topic, which is LAN technologies in the GATE syllabus. So before we go for this actual LAN technologies, we'll just look at what exactly is the data, how you are going to transmit the data over a transmission medium. So the data which you are going to represent in your system is in the form of is the digital data that you are going to represent. That is, it takes the values of ones and zeros only. So you are going to represent all the data in terms of bits. A bit is the smallest element of the data that you are going to have here. So when you are transmitting the data, these bits are to be transmitted from the source to the destination. But over a transmission medium, it has to be transmitted. But this transmission medium can allow the data to be transmitted in the form of an electromagnetic signal. So in order to transmit the data, you need to convert the data. You need to transform the data into electromagnetic signals. So how your digital data is going to be transmitted in the form of this electromagnetic signals. So you can represent the signals in the either as an analog signal, or it can be a digital signal that you can represent your information as. So when you go for an analog signal, it is a continuous data, a continuous wave that you are going to have. So that is how you are going to transmit the data. But when you go for digital signal, it is in a discrete format that you are going to transmit the data here. So when you go for these digital signals, so you are going to represent these zeros and ones, which are your values that the bit can take. A bit can take a value of 0 or 1. So when you are representing the data when you are representing the data, so it will be either 0 or 1. The bit can take a value of 0 or 1. So when you are representing a 0, so it can take a voltage of 0 to represent 0, and it can take a value of plus 5 volts or say some positive voltage to represent a value of 1 over here. So here the number of levels that we have are 2. One is a 0 voltage and the other level is some positive voltage, maybe 5 volts that we have taken here. So plus 5 volts represent 1 and 0 volts represent a 0 voltage over here. So these are the two levels that we have here. So even you can represent a digital signal in more than 2 levels also. So when you are representing a digital signal in more than 2 levels, that can carry more than 1 bits on each level. So we'll just have a look at a diagram and then it can be easily understood. So here you can see that there are 2 levels that we have here, a 0 voltage and maybe a positive voltage here, say for example 5 volts here. So 5 volts represent 1 here and 0 volts represent a value of 0. So this is a stream of bit that we have. So per every second, 8 bits are getting transmitted over here, say. Then the bit rate is number of bits transmitted per second is the bit rate here. So there are 8 bits that are being transmitted over here, and hence the bit rate is 8 bits per second here. So as the 8 bits are sent in 1 second, the bit rate is 8 BPS that you are going to call it as. So this bit rate is the number of bits that are being transmitted per second. So in this second, 8 bits are transmitted. These are the 8 bits that are getting transmitted. And when you represent them as a signal, this is how we are going to represent this data in the form of a signal here. So 1 represents a positive voltage and 0 represents a 0 voltage here. So this is how the data is getting transmitted here. So this is one period that you are going to have. So this is repeated over here. These periods are repeated. This is the time slot that you are going to have here. So this is how the data will be transmitted over in the form of a digital signal from source to the destination here. So here you are making use of 2 levels. So when you are having 2 levels, you can represent either 1 or 0, making use of these 2 levels. In this example, you can see that there are 4 levels. Maybe this is plus 4 plus or 4 volts, and this is plus 2 volts, and this is minus 2 volts, and this is minus 4 volts, say for example. So these are the 4 levels that we have here. So the level 1, in the level 1, which is minus 4 volts, the data that is getting transmitted is 0, 0. So here you are transmitting 2 bits per period or per cycle here at a time here. And here level 1 represents 0, 1, and level 3 represents 1, 0, and level 4 is 1, 1 that you are going to have here. So these are the 4 levels. When we look at this, with these 4 levels in a period, you are going to transmit 2 bits simultaneously here. So when you represent it in a generic form, if you have n number of levels, n levels that you have, then the number of bits that you can transmit is, the number of bits that you can represent is log n base 2, right? So when you are having 4 levels, it is n is equal to 4. So log 4 base 2, which comes to log 2 to the power of 2 base 2, which goes to 2 here. So you can have 2 bits being represented here, making use of this 4 levels. Here, when you look at this, it is 1 bit that you are going to have here, because the levels are 2. So log 2 base 2, that gives us a value of 1. So this is an example. A digital signal has 8 levels. How many bits are needed per level? So how do we calculate this? We know that if n is the number of levels that you are going to have, the number of bits per level will be equal to log n base 2. What is n here? N is 8 is the number of levels that you are having here. So it will be equal to log 8 base 2, which is equal to log 2 to the power of 3 base 2, that is equal to 3 into log 2 base 2. So log 2 base 2 is nothing but 1. So it will be 3 into 1. So it comes to 3. So each signal level is represented by 3 bits here when you go for this 8 number of levels. So try it on your own now. I'll give a minute. A digital signal has 9 levels. How many bits are needed per level? Just give a try. So just give a try for this. So this is log 9 base 2, right? Where n is equal to 9. So this is log 9 base 2 that you are going to have. So what is log 9 base 2? So this is not an integer that you are going to get here. Rather, you will be getting something like 3.1 or something like this. So when that is the case, how do you represent how many bits that you require? But when you represent the signal, it should be in powers of 2 only that you need to have here. So 2 to the power of 3, when you take, it comes to 8. So you can represent only 8 levels, but you have 9 levels to be represented here. So it will not be possible with 3 bits. Rather, you need to go for the next integer here, which is 4. So 2 power 4 is 16, but some may be wasted. But to accommodate these 9 levels, you need to make use of 4 bits here. So the answer is 4. Clear? So we'll go on to the next one. So before we go for this, we'll just have a look at the various terminology that is being used here. So previously we have seen what the bit rate is. So the bit rate is the number of bits of data that is being transmitted per second. We call it as a bit rate. So now, in addition to this bit rate, we also have what is known as a baud. When you are representing the data in the form of a signal, you may be representing that signal. There may be several changes in the signal that may happen per unit per second. So how many number of times per second a signal is getting changed on a transmission line, we call it as a baud. So here in this particular case, when you go for this, so one level is represented at level 1 only. So the baud here is equal to the bit rate that you are going to have here. So the number of changes that per second that you are going to have on a transmission line, we call it as a baud. So when you go for a bandwidth, so when you are representing the signal, so you are going to represent it in the frequency domain. So when you are representing this, the bandwidth is the difference between the highest and the lowest frequencies that are contained in that signal. Or we can describe it as the maximum bit rate that a network can be able to offer. We call it as a bandwidth. So these are the terminology that are very much essential to note. So, and the other thing that we have to know is the baseband transmission. So when you go for this baseband transmission, so whatever cables that we are making use of, the coaxial cable or that is required in Ethernet, we are going to make use of this baseband signaling over there. So what is this baseband signaling? The data from the sender to the receiver has to be transmitted over a transmission medium or a channel. So this, when you are representing this data in the form of a digital signal and it is not converted into analog signal, then we call such a signaling as a baseband signaling. So sending a digital signal over a channel without changing the digital signal to analog signal, we call it as a baseband signaling. So when you go for this baseband transmission, the required bandwidth will be proportional to the bit rate. If we want to send the data at a faster rate, then we require more bandwidth. So that is obvious, right? So the other one, so when you are considering the efficiency of your network, so we are looking at how fast the data is getting transmitted over your communication channel. So that is a very important consideration that we have to look into when we talk about data communications. So how fast can we transmit the data? So that you're going to represent in terms of number of bits per second over a channel. So this data rate, it depends on three factors. The first factor is the bandwidth which is available and the number of levels of the signal that we make use of for transmitting your data and the quality of the channel. So these are the three factors based on which the data rate is affected here. So it depends on these three factors here. So when you go for this three factors, the last factor when you look at it depends on the quality of the channel. So if the channel is providing lot of noise in the sense some sort of disturbance that you are going to have in the channel, if the noise is getting added to the data, then there will be some sort of degradation in the signal. If that is the case, your data will not be received properly at the destination. So we should see that the channel which you are selecting should have low noise here. That is why most of the networks right now are making use of this fiber optic cables which are having high SNR ratio. So what is this SNR? Signal to noise ratio. So the signal, if it is greater than 1, it indicates that greater than or equal to 1, then it indicates that the noise that is getting added to this is less when compared to that of the signal. So if this SNR ratio is less than 1, in the sense the noise is greater than the signal and hence you will not be receiving the data correctly over there. So based on this, your data rate changes over here. So the channel can be either a noiseless channel or it can be a noisy channel. So if it is a noiseless channel that you are going to have, then the maximum data rate that can be obtained is given by Nyquist bit rate. So Nyquist has given a formula to calculate the maximum data rate on the channel given the bandwidth and the number of levels that you are going to have, and this signal noise you are not considering over here as it is a noiseless channel. And to add up this noise also to the channel, Shannon has given a equation to calculate the maximum data rate of the channel when in a noisy channel here. So these are the theoretical maximum bit rates regarding the noiseless channel and a noisy channel. So in the noiseless channel, the Nyquist bitrate formula is maximum bitrate is equal to 2 into the bandwidth into log L base 2, where L is the number of levels of bit representation, number of signals that you are level of signals that you are going to have here. So 2 into bandwidth into log L base 2 is the formula to calculate maximum bitrate in a noiseless channel. And when you go for a noisy channel, then you are going to consider the noise also. So for that, we will be considering this signal to noise ratio. So here the bitrate, the maximum bitrate will be equal to bandwidth into log S1 plus SNR base 2. what is signal to noise ratio? 1 plus signal to noise ratio log base 2. This is the formula for calculating the maximum bit rate of a noisy channel given by Shannon. So that we call it as a Shannon capacity also. So for this is a simple example. Consider a 3 kilohertz noiseless channel, that is 3 kilohertz is the frequency noiseless channel transmitting a signal with 4 signal levels. For each level, we send 2 bits here. So the maximum bit rate can be calculated as, so this is a noiseless channel, so you need to make use of Nyquist bit rate here. So bit rate, maximum bit rate is equal to 2 into bandwidth into log L base 2. So that is calculated as 2 into, so this is the frequency, 3000 kilohertz is the frequency, 3000 into log 4 base 2. So this comes to 2 into 2 into 3000, so it comes to 12,000 bits per second. So that is the maximum data rate over a noiseless channel. So now we'll consider one example, another example here. So we need to send 265 kbps over a noiseless channel with a bandwidth of 20 kilohertz. So how many signal levels do we need here? So we make use of the Nyquist formula for this, because it is a noiseless channel that you are going to have. So we need to make use of Nyquist criteria, Nyquist formula for this. So 265 kbps is the maximum data rate that is achieved. So 2,65,000 is equal to 2 into 20 kilohertz, 20,000 into log L base 2. So what is this L you need to calculate here? So when you substitute these values, you will be getting L is equal to 2 to the power of 6.625, which is coming to 98.7 levels. So the resulting that you have is not a power of 2. This is not a power of 2 here. So what you need to have here, so you need to either increase the number of levels or you need to reduce the bit rate here. So if you are going to increase the number of levels, the nearest to 2 powers for this 98 is 2 to the power of 7, which comes to 128 levels here. So this is 128 levels that you are going to have, and the maximum bit rate that we can get out of this 128 levels is 280 kbps. Or if you reduce this number of bits, then the nearest on the nearest lower value that you are going to have is 6 here. 2 power 6 is 64 here. So 64 levels, and the bit rate is 240 kbps that we can achieve here. So this is the maximum bit rate over a noiseless channel. So now we'll consider another example here. So just do it for yourself. I'll give you a minute. Consider a noiseless channel with a bandwidth of 3000 Hz transmitting a signal with 2 signal levels. Now the signal levels are just 2. So what is the maximum bit rate? So in the previous case, we have considered 4 signal levels. Now it is just 2 signal levels that you are going to have here. So now what is the maximum bit rate here? So the maximum bit rate is 2 into 3000 into log 2 base 2. So that comes to 6000 bits. So this is the Nyquist formula that has to be applied here, 2 into bandwidth into log n base 2. Right? So we'll look at the next example wherein you're going to consider a noisy channel here. So we have a channel with a 1 megahertz bandwidth. The signal to noise ratio for this channel is 63. So this is the signal to noise ratio that is given as 63. And what is the maximum bit rate of the channel? So what is the maximum bit rate of the channel that you need to find out here? So what will be the maximum bit rate of the channel? So here it is a noisy channel that we have considered. So you need to apply Shannon capacity over here, equation here. So the Shannon capacity equation is P into bandwidth into log 1 plus SNR base 2. So this is the formula that you need to apply. Bandwidth into log 1 plus SNR base 2. What is SNR? SNR is given as 63. So this will be, the bandwidth is 1 megahertz, 1 into 10 to the power of 6 into log 1 plus SNR is 63. So 1 plus 63 is 64, which is represented as 2 to the power of 6 here. So 2 power 6. So this comes to 6 into log 2 base 2. So it comes to 6 here. 6 into the bandwidth is 1 megahertz. So it comes to 6 megabits per second. So that is the solution for this, where you are considering a noisy channel here. Here the SNR ratio is directly given as 63 here, but sometimes SNR ratio will be given in terms of decibels. So when it is given in terms of decibels, you need to convert that into the ratio value here. So say for example, if it is given as something like 1 decibel, then in that case, it means that log S by n base 10, 10 log S by n base 10 is equal to 1. So that implies, so this comes to log S by n base 10 is equal to 10 to the power of minus 1 when it goes over, 10 goes over here. So I'll just show you. So it comes like this. So when the SNR is given in terms of signal to noise ratio is given in terms of decibels, then it is like 10 log so 10 log 10 base 10 is given. Say for example, it is given as 1. When it is given as 1, this implies S by N is equal to signal to noise ratio SNR is equal to when this 10 goes over here, then it becomes 10 to the power of minus 1. So when it becomes 10 to the power of minus 1, it becomes 10 to the power of minus 1. So now this is log 10, log SNR base 10. So that is what you have here. So this implies that SNR is equal to, when it goes over here, it will be 10 raised to the power of 10 to the power of minus 1. So 10 raised to the power of 0.1. So that is what is given. So that is what you are going to have here as a SNR value. So you need to be careful when the SNR value is given. So is it given in decibels or is it given directly? That you need to consider here. So if it is given in decibels, then this is what is given. 10 log S by N base 10 is given. Now you need to convert it into SNR and then you need to get this value over here. Clear? So this is about the signal maximum bit rate being considered when you go for this noisy channel. So in a noisy channel, you are going to apply this Shannon criteria over there. So next we'll move on to the other parameters which affect your network. So the important issue in networking is the performance of the network. So how good is your network? Maximum bitrate is one that we'll be expecting out of a network. And apart from this, so what are the other parameters that we have to estimate the performance of a network? So it depends on the bandwidth. The bandwidth is one, and then that is the maximum data rate has to be more here. So and then the throughput, the number of bits that you are going to transmit per second is the throughput. That should be high. So you should have maximum bandwidth and you should have the maximum throughput. If you are going to have this, then your network is performing a better one. And the latency, or we call it as a delay. So this has to be less. So these are the parameters based on which you're going to decide how good is your network. And of course, you're going to decide on the volume of your network based on by taking the product of bandwidth and delay. So these are the 4 parameters that estimates the performance of your network. So now, what are these parameters? So the bandwidth, as we said, in the previous case, it is the difference between the maximum frequency and the minimum frequency of a signal, so which is represented as hertz. And this maximum, the bandwidth, or it can be a maximum data rate of a channel. So this is represented, the bandwidth utilization should be high. And when you go for the throughput, it is a measure of how fast you can actually send the data from one end to the other end through a network. So we may have a link. The bandwidth may not be utilized completely over here. So you may have a link with a bandwidth of 1 Mbps, but we can send only 300 kbps here. Sometimes you may not be utilizing the entire bandwidth, so only a part of the bandwidth will be utilized. So the throughput will be 300 kbps here. So per second, you are able to transmit 300 kbps, even though the channel can transmit 1 to 10 to the power of 6 bits per second. It is not able to transmit at that particular level. So the throughput is less than the actual bandwidth, that is actual maximum data rate that can be possible here. So this throughput has to be high so that we can effectively utilize the entire bandwidth. The other parameter is the latency. So it defines as how long it takes for an entire message to be transmitted completely, to completely arrive at the destination from the time the first bit is sent from the source. So when you are transmitting, say for example, when you are transmitting a data which is of 1000 bits, so the first bit gets into the channel here. All the 1000 bits have to be placed onto the link first. So the time it takes to place all these 1000 bits onto the link, we call it as a transmission time. If it is a frame, we call it as a frame transmission time. So the first bit has to reach to the destination. It takes some time for the first bit to reach to the destination, and that time we call it as a propagation time. The time that elapses for the first bit to start from the source to reach to the destination, we call it as a propagation time. So these two are very much important. The transmission time, placing the entire frame onto the channel or onto the link, we call it as a transmission time. So that depends on the length of your the size of your packet or the size of your frame. So the entire message has to be placed onto the channel. So the time it takes for the entire packet to be placed onto the channel is transmission time. So it depends on the size of the packet and also the data rate, the maximum data rate that your network is offering, and hence the transmission time is defined as the length of the message divided by the bandwidth of the channel here. So that is the transmission time. And the other time is the propagation time, how long it takes for the first bit to be transmitted to the other end from the source to the destination. So that depends on the distance between the source and the destination, and also at what speed the data is being transmitted from the source to the destination. So the propagation time will be equal to the distance between the source and the destination divided by the speed at which the data is being transmitted. That is the propagation time. So these two times are very high when compared to that of the other times. And these times, queuing time and the processing time, they depend on the intermediate nodes that you are going to have here. So the queuing time here. So when you are transmitting the data, here the data is not directly transmitted from the source to the destination. As we may see that there are a number of intermediate nodes that we have. So all these intermediate nodes, they'll be getting the data, and then they'll be getting the data from one link, and they have to place it onto the other link over here. So they take certain time over here to process this. So that is the processing time here. So getting the data from one link, and then it has to be placed onto the next link here. So that depends on how fast these intermediate nodes will be processing the data. And the queuing time also, maybe that link can be involved, that particular node can be involved in transmitting the data from various nodes over here, and then it has to be processed onto a single channel output, say. Then in that case, all the packets coming from various nodes will be queued over here, or lined up over here at this intermediate node. So for the packet to be transmitted, when it is in the queue, it has to come to the beginning of the queue, and only then it gets processed. So how long this packet will be staying in the queue for getting processed? So that is what we call it as a queuing time here. So these two, queuing time and the processing time, they depend on how the intermediate nodes over here. So generally, when you are calculating the latency, you need to calculate all these four here, but mostly in our calculations, we'll be doing this based on the propagation time and the transmission time. So that is the latency. So the next one, the next performance factor is the bandwidth delay product. So that indicates the number of bits that can fill the entire link. That is, the volume of the link can be measured by taking the bandwidth and the delay product here. So in the sense, so when you are talking about the bandwidth, this is the maximum data rate that you are going to offer. So for example, you can offer 10,000 bits per second. That is, your channel can transmit 1,000 bits per second, and the latency is something like 10 milliseconds or so, say. Then if you are going to multiply, so at a time in the channel, you can have these number of bits. So that is what we call it as a volume. So this is bandwidth delay product that you are going to have here. So the bandwidth and throughput has to be maximized, and this latency has to be minimized, so that the performance of your network will be better here. So these are the delays that I am talking about. The transmission delay, propagation delay, queuing delay, and the processing delay. So when you go for the transmission delay, so this is the time taken, as I said, to transmit the packet onto the outgoing link. The entire packet has to be placed onto the link here. So how much time it takes, that is the transmission delay. So the transmission delay depends on the length of the message and the bandwidth. So transmission delay is equal to the size or the length of the message divided by the bandwidth. And the propagation delay, it depends on the distance between the two nodes and also the transmission speed. So the propagation delay is equal to distance divided by the transmission time. And the queuing delay is the time spent by a packet waiting in the queue for processing. It depends on the congestion in the network. That is what I am speaking about. In the intermediate node, there may be number of packets that may be coming in to get processed at this intermediate node, and in that case, it is getting congested over here. So the delay that is introduced at the intermediate nodes here, and then the processing, the time taken by the processor to process the data. So all these are being included in calculating the latency. So this processing delay depends on the speed of the processor. So both the queuing delay, as I mentioned, queuing delay and the processing delay are dependent on the state of the system. So the bandwidth is always, when we look at the bandwidth, is always expressed in powers of 10 only. When we say it is 1 KB, then it means that you are going to have 10 to the power of 3. bits per second. 1 kbps, then it is 10 to the power of 3 kbps. But when we talk about the data, it will be in powers of 2. When you say 2k, 2 kb, 2 kb, then it means that 2 into 2 to the power of 10 bits that you are going to have here. So when we look at the optical fiber cable, the transmission speed of the data packet over a optical fiber cable will be equal to 2.1 into 10 to the power of 8 meters per second. Why this is? So the fiber on the light is traveling at a speed of 3 into 10 to the power of 8 10 to the power of 9 meters per second. But here you are going to consider only 70% of this maximum data rate that you are going to consider, 70% of the speed that you are going to consider over here in a speed of the light that you are going to have in the fiber optic cable. So it comes to 2 to the power 2.1 into 10 to the power of 8 meters per second. That is the transmission speed of the data packet in a optical fiber cable. So we'll just have some examples regarding the performance issues here. So a network with a bandwidth of 10 Mbps can pass only an average of 12,000 frames per minute. It is number of frames that you are going to transmit per minute, with each frame carrying an average of 10,000 bits. So what is the throughput of this network? So just I'll give a minute. You just look into how you can solve this. So what is given? The bandwidth is given. Bandwidth is given to be 10 Mbps, 10 into 10 to the power of 6 Mbps. And the average of 12,000 frames per minute are being transmitted. Each frame is of 1,000 bits. So the size of the frames, total size of the frames in bits is 12,000 into 10,000. But it is given per minute. So now you need to convert it into per second. So it will be 12,000 into 10,000 divided by 60. So that gives the number of bits that you are going to transmit per minute. So this is the actual utilization of the channel. And when we look at the actual bandwidth, so this is the actual bandwidth, 10 Mbps. But the entire 10 Mbps is not being used over here. So it is making use of only 12,000 into 10,000 divided by 60. So that is the maximum utilization of the channel. And that is the throughput. So 12,000 divided by 60 into 10,000. So it comes to 2 Mbps. So when we look at what is the efficiency of this channel, so actually you can transmit to a maximum of 10 MB per second, but the channel is utilized only to transmit 2 MB per second. So the efficiency will be equal to 2 divided by 10. So it comes to 1/5. So 1/5 of the channel is being used, only 1/5 of the capacity of the channel is being used for transmitting your data. So this is how you are going to calculate the throughput and the efficiency of the channel. So another example. So what is the propagation time if the distance between the 2 points is 12,000 kilometers? So assume the propagation speed to be 2.4 into 10 to the power of 8 meters per second in the cable. So how is it that you are going to calculate this? So the distance is given, the propagation speed is given, so you are expected to calculate the propagation time. So what is propagation time? The propagation time is equal to distance divided by the speed. So what is the distance? 12,000 kilometers. And what is the speed? 2.4 into 10 to the power of 8 meters per second. So this is in meters and this is in kilometers. So you need to convert this kilometers into meters. So the distance will be 12,000 into 10 to the power of 3 divided by 2.4 into 10 to the power of 8. So what it results? It results in 50 milliseconds. So 12,000 into 10 to the power of 3 by 2.4 into 10 to the power of 8. So you'll be getting this as 50 milliseconds. Clear? Now, so we'll go to another example. So what are the propagation time and the transmission time for a 2.5 kilobytes message? Here you need to be careful when you are reading the question whether it is given as bits or a bytes. That has to be taken into consideration. Otherwise, will result in a different value here. So it is 2.5 kilobyte message if the bandwidth of the network is 1 Gbps. So what is the propagation time and the transmission time? For a 2.5 kilobyte message, if the bandwidth of the network is 1 Gbps, assume that the distance between the sender and the receiver is 12,000 kilometers and that the light travels at 2.4 into 10 to the power of 8 meters per second. This is what is given. So in order to calculate the propagation time, what is that you require? You require the distance and the speed. So what is the distance? Distance is 12,000 kilometers. So 12,000, convert it into meters by multiplying it with 1,000 divided by, so what is the speed of the light? It is 2.4 into 10 to the power of 8. So it comes to 50 milliseconds. And the transmission time will be equal to the length of the frame, the length of the message divided by the bandwidth. So what is the length of the message? It is 2.5 kilobytes. So 2500 is the 2500 bytes here. 1 byte is 8 bits. So 2500 into 8 divided by the bandwidth. Bandwidth is 1 Gbps. So 1 GB in the sense 2 to the 10 to the power of 9. So you'll be getting 0.02 milliseconds. So this is how you are going to calculate the propagation time and the transmission time. So making use of them, we'll be now going into the other part of this. So the second layer that we have is the data link. From the bottom of your OSI model or the TCP/IP reference model is the data link layer. So what is the functionality of the data link layer? So the functionality of the data link layer is to form a frame by adding a header on the trailer to indicate the fixed bounds for this message that you are going to transmit here, and that this data link layer will be offering the services only between two adjacent nodes. So along with this framing, it also offers as flow control and the error control. So error control in the sense when the data is transmitted, maybe few of the data may get dropped over here or it may be received at the other end with some disturbance in the data here. So some errors that may be introduced, so you need to identify the errors, or if at all the packets are lost, the data is lost in between, then also you need to identify and then you have to retransmit it here. So that all will be dealt in error control. And the other one is a flow control. So this is running between two processors here. One processor, the sender processor, if it is transmitting at a faster rate and the receiver is a slow processor which is not able to get the data at that particular rate. If that is the case, then this receiver will be overdumped with the data by the sender. There should be a means by which the receiver has to specify the sender that it is not able to process at that particular rate, and hence you are going to have some sort of flow control here in order to avoid the speed mismatch between the sender and the receiver. So never a receiver has to be overdumped with the data from the sender. So that we are going to deal in the flow control. So these are the various functions that the data link layer has to offer. Apart from this data functions, so what has to be done is, so if you are going for a multi-access channel, so when you are having a multi-access channel, in the sense a single channel being used by number of nodes connected together, if that is the case, then there may be some sort of disturbance that may occur over here. That is, say for example, if two nodes simultaneously wants to transmit here. So they'll just send the data that is similar to that of two people shouting at a time. Then we will not be able to listen what a particular person is talking to. In the similar way, when the data is being dumped by two nodes simultaneously on the channel, there will be a collision here. So you need to avoid this. You need to resolve this. So for that, you need to have some sort of mechanism at the data link layer to deal with the resolving this access in a shared medium, and that has been introduced in the form of a multiple access MAC layer that you are going to have, medium access control layer. So that has to be done by this at the data link layer. So at the data link layer, it is divided into two sublayers. One is the logical link control sublayer, and the other one is a MAC sublayer that you are going to have here. So medium access control sublayer that you are going to have here. So when we look at the IEEE standards for this LAN, so 802 is a project under which all the topologies that we make use of in the LAN are being standardized. And there are various topologies that the LAN can have here, like the bus topology, it may be a ring topology, or it can be a star topology, or whatever topologies that we have here. So for all of them, to deal with all of them, we are going to have a different MAC sublayer over here, and this is being defined in the IEEE standards here. So 802.3 is the standard that is being defined for this Ethernet, and for the rest it is being defined 802.4.5, like this it goes on here. So the logical link control, you can see that there is a single logical link control here at the data link layer, and at the bottom layer, the MAC layer, it depends on the type of topology that you are going to have. The MAC sublayer will be having its own protocols over here, and the bottom layer, also the physical layer, also corresponds to the corresponding MAC layer protocol that you are going to make use of here. So this is the IEEE standard for LANs. So the data link layer is divided into two sublayers: logical link control sublayer, which provides us all the functionality like the framing, flow control, error control will be done by the logical link layer. So to deal with the multi-access channels, we have a medium access control layer, and that depends on the topology that you are going to make use of here. So these are the IEEE standards that are being defined. So when you go for this Ethernet, this is 802.3 that you are going to have here. So when we look at the evolutions of the Ethernet is nothing but a common bus topology that you are going to have here. So when you look at the evolution of the Ethernet, so it started with a standard Ethernet, which has offered to a maximum of 10 Mbps. That is the maximum data rate that is being offered by the standard Ethernet. Later on, there are a number of improvements that are being made, and then it resulted in a fast Ethernet, which is 100 Mbps. Now, whatever we are making use of now is the fiber optic cable that you are making use of now. It is providing us us with a gigabit Ethernet here. And the 10 gigabit Ethernet will be in the, even this will be in the near future that you are going to have this 10 gigabit Ethernet. So when we look at the distance, how far this Ethernet, this standard standards can work here. So when you go for 10 Mbps Ethernet, so it can operate up to a distance of 2,500 meters. And when you go for 100 Mbps Ethernet, it offers us, or it can operate to a maximum of 250 meters, and 1 Gbps Ethernet, it operates to a maximum of 25 meters that you're going to have here. So before we go into the standard Ethernet, so we'll just have a look at the 802.3, that is the Ethernet frame format. So how you're going to transmit the frame over here. So this is the format of the frame that you are going to have. So these two, the frame that we can see, this is the frame format that you are having here. So we have seen that at the data link layer, there is a header and the trailer that is getting added to the data that is coming from the network layer. So if this is the data that is coming from the network layer to be transmitted, then to this you are going to add a header and a trailer is being added here at the data link layer. So when you go for this 802.3 MAC frame format, this is the format of the frame, and this is the header and this is the trailer that you are going to have. In addition to this, we have shown two fields over here. These fields are getting added at the physical layer. And when we look at these fields, the first field is the preamble, which is of 56 bits here, which contains alternate ones and zeros. So this is 7 bytes that you are going to have. This is used in order to alert the receiver that the data is getting transmitted, and also for the synchronization between the sender and the receiver, you are going to make use of this preamble. And the next field is the start frame delimiter. This is 1 byte here. So after this 7 bytes of preamble, it will be immediately followed by this start frame delimiter, which is of 1 byte. The only difference between these 2 bytes here is, so this preamble is alternate ones and zeros that you are going to have, even as the SFD also will be having alternate ones and zeros, except that the last bit that you are going to have is set to 1 here when you go for this SFD. So these 2 fields are getting added at the physical layer for synchronization and to indicate the beginning of the frame over here. And now actual frame is this. So this contains the header, which is of 14 bytes, and the trailer, which is of 4 bytes that you are going to have. So this 14 byte header that you are going to have here is the first 6 bytes forms a destination address, and the next 6 bytes are the source address. So this is a Ethernet that we have set. So the Ethernet addresses that we have are 48-bit in size, and hence they will be occupying 6 bytes here. And the source address is also 6 bytes. So who is the sender and who is the receiver that you're going to have here. And remember, on every hop, these will be getting modified when the data is transmitted from a source to a destination, which is on a remote network here. So the source destination address, these are the physical addresses here that you are going to have. And the next part is the next field is the length or the type field, which is of 2 bytes in size. So previously in the old versions of this Ethernet, it was used for the type here, which indicates what type of upper layer data is being carried in this particular frame. Now it has been replaced with the length, which indicates what is the total length of the data that you are going to transmit over here. So that is the length field that you are going to have here, and next followed by the data. So this is the data that you are going to get from the upper layer, which is encapsulated into a frame over here. So this data, it has a maximum and a minimum limit on the data over here. So the maximum limit that you can have here in a 802.3 frame is 15,000 bytes, and the minimum length is 46 bytes. Why there is a restriction on the size of the packet that you are going to have here? The restriction is that when you are having a maximum size, this is the maximum size that we specified, 1500 bytes is the maximum size of the data that you can transmit in a single frame. Why this limit has come here? So when they have introduced this Ethernet, at that time, the memory was very costly here. So when a frame has to be transmitted, when a frame is transmitted, it has to store the frame, because if at all any error happens in between, it need to retransmit it. So it has to store the frame at the centers, and if the frame is very large, then it occupies large memory over here. That is one reason why they have restricted the maximum payload. And the other reason is, if at all the size of the frame is very large, then if a channel or if a station acquires this chance of transmitting the data, then it monopolizes the entire channel here. So it takes a lot of time for that to transmit a very large frame, and the other stations may be starving for the channel here. So for that purpose, they have limited the maximum size of the frame. So the maximum size of the frame is 1518 bytes, including the header and the trailer. So the maximum size of the data that you can have is 1500 bytes over here. And there is a restriction even on the size of the minimum size of the message also. So the minimum pad length has to be 46 bytes here. So that depends on the protocol that you are making use of. So this Ethernet that we have, it makes use of CSMA-CD protocol, which imposes a maximum limit on the size, minimum limit on the size of your frame. So this is 46 bytes. So when we look at CSMA-CD protocol, we will explain why this limit has come over here. The minimum limit, the minimum payload is payload length should be 46 bytes. That we'll explain later. So this data, if it is less than 46 bytes, what has to be done? So you need to add some sort of zeros over here so that the minimum data can be 46 bytes. And this length, it specifies what is the actual length of the data that is being transmitted here before padding. So this gets padded so that it becomes, if the data is less than 46 bytes, then you have to pad it so that it becomes 46 bytes over here. So this is the size of the frame that you are going to transmit, whose maximum length is 1518 bytes, including the header and the trailer. And the minimum length of the frame is 64 bytes, including the header and the trailer, which results in a 46 bytes of payload here. And the last field here in the MAC frame is CRC, that is cyclic redundancy check. This is used for error control. So it verifies whether the data has been received intact without any modifications over here or not. That will be checked upon. If at all it is an error, if the CRC does not match over here, then it indicates that there is an error during the transmission. And the data link layer in this particular case will request the sender to retransmit the frame, or it simply drops the packet, and then when the timer times out at the sender's end, it is going to retransmit this particular frame here. So this is how error control is being done. So the CRC generally, the error control message, which the CRC that you are going to have, will be appended only at the end, not at the beginning of the frame. Why? Because whenever you receive the data, so it will be easy to process the data over here. So as soon as you receive the data, you are going to calculate this checksum here, and hence you need not have to store it again and then recalculate the checksum. That is, you need not have to reprocess it again so as to calculate, to verify the checksum. So as soon as you get the data, you will be able to process it for calculate the checksum over here. That is why you are going to place the CRC at the end, not at the beginning. If at all you place it at the beginning, until you get the entire frame, you have to get the entire frame, and then you have to reprocess it, and then you need to check the CRC here. That is why you are going to have it at the end. So this is the format of 802.3 MAC frame. So we were talking about these addresses here. So in the last class, we have seen that the Ethernet addresses are of 48 bits. So these are 6 bytes that you are going to have here, and those are represented using the colon notation here. So these are the 6 bytes that you are having, and these bytes are separated by the colons, and this byte is represented as a 12 hexadecimal digit here. So 2 digits that you are going to have here, so which results in 48 bits that you are going to have. So when you look at what sort of address it is, the address can be either a unicast address, that is only to a particular node, or it can be a multicast address to a group of nodes. So that can be decided based on the first byte in Ethernet address. So in the first byte, if the least significant bit holds a value of 0, then it indicates that it is a unicast address. If it holds a value of 1, then it indicates that it is a multicast address that you are going to have here. So the least significant bit of the first byte, it defines the type of address. If this particular bit is 0, then it indicates that it is a unicast address. Otherwise, it is a multicast address. And the broadcast address is a special case of this multicast address, wherein all the bytes that you have here, all the 6 bytes, if they are set to 1, all the bits, all the 48 bits, if they are set to 1, then it is a broadcast address that you are going to have. So this is a special case of broadcast destination address, is a special case of multicast address in which all the bits are set to 1. In any case, the sender address, the source address that you are going to have should always be a unicast address, because the packet can originate only from a particular sender. So the source address should be a unicast address, and the destination address can be either a unicast address, or it can be a multicast address, or it can be a broadcast address also that you can have. So here is an example that we have. So define the type of the destination address here. So if this is the destination address, this 4A is the first byte that we have. How do you represent this A? A is 10, a value of 10 that you are going to have here. So that is represented as 1010 here. So 1010, what is the least significant bit? The least significant bit here is 0. So when it is 0, it indicates that it is a unicast address. In this particular case, 7 is represented as 0111. So the last bit, the least significant bit here is 1. So, and hence this is a multicast address. In this particular case, all bits are 1s. So F is all 4 1s that you are going to have. So all bits and all the 6 bytes are 1s, and hence this is a broadcast address. So when you are transmitting this address, so how are you going to transmit it on a line here? So it is not transmitted like like the first bit here in this as the first bit as the output over here. Rather, the addresses are sent from left to right, byte by byte. That is, the first byte is transmitted first, then the next byte here, it goes on from left to right. But when you are transmitting the bits within a byte, this is done from right to left here. From right to left. That is, 7 is represented as 0111 and 4 is represented as 0100. So when you are transmitting this, first the value of 7 in the reverse order is transmitted. That is, the 7 value is 0111. So this last 1 is transmitted first. So this is 7, 0111 is 7. So you will be transmitting 1111, 1110 and then 4. So 4 is 0100. So that also in the reverse order, 0010. So this is how we are going to send the send this Ethernet address on the line. So that is about the frame format, Ethernet frame format that we have. And when we look at the standard Ethernet, so coming to the standard Ethernet, it offers us 10 Mbps speed. That is the maximum data rate that can be achieved by making use of the standard Ethernet. So there are 4 implementations of the standard Ethernet that are available. One is 10 base 5. So this makes use of these two, 10 base 5 and 10 base 2 are dependent on the bus topology, and the other two, 10 base T and 10 base F, they follow the star topology. And the cable that you are going to make use of here is a thick cable when you go for a 10 base 5. And this 10 here indicates that the maximum data rate that you can achieve is 10 Mbps. So this 10 indicates it is 10 Mbps data rate, and that this base indicates that you are going for a baseband signaling over here, and this 5 indicates that this is the maximum segment length that you can have. That is, this particular network can go to a maximum, can be extended to a maximum of this particular distance, 500 meters here. So this is 10 base 5 that you are going to call it. which makes use of a thick coaxial cable. So when we look at a thick coaxial cable, it will be very difficult for us to bend this here. So when you are laying this thick coaxial cable, if it can be laid in a single floor, you can do it. But if you want to bend it, it is not possible. So we'll not be making use of this 10 base 5. If at all, the land has to extend to various floors in a building. So there we'll be going for this 10 base 2, which is the cable here is a thin cable that thin coax that you are going to have, and that can be easily bended. So when you go for this 10 base 2, it indicates 10 indicates that it is 10 Mbps data rate, and this uses baseband signaling, and this 2 indicates that to a maximum of 200 meters it can go here, but it is not 200 meters, rather it is normalized to 200 meters. It is just 185 meters that you can have here. And the other one is 10 base T. This T indicates that it is making use of a twisted pair. So the twisted pair is another form of guided media that we have here, wherein you are going to have two wires which are shielded, which are twisted over here. So as you have more number of twists in a pair, in this twisted pair, the noise that gets added to this is getting reduced over here. So here the twisted pairs are of two types. One is a STP and the other one is a UTP. So when you go for shielded twisted pair, so these two cables are being shielded by another layer over there. So that is shielded twisted pair, and the other one is UTP, is the unshielded twisted pair that you are going to have, where there won't be any other protective material that we have, which will be protecting this pair of cables that you are going to have here. And the other one is 10 base F. This is another implementation. These two star topology here, and this F stands for the fiber cable, and this also offers a maximum data rate of 10 Mbps and makes use of baseband signaling here. So the encoding that is used in the standard Ethernet implementation is how you are going to represent the bits. It makes use of Manchester encoding here. So at the sender's end, you need to encode your data. You're making use of some encoding format, and this is the encoding format that is being used by the standard Ethernet, which is a Manchester encoding. So when you go for this Manchester encoding, so the bit 0, you can see that it is represented as it starts with a positive voltage, and then in the half period it comes down and it goes to the negative voltage here. So this is the representation for 0. And 1, when you look at, it starts at the negative voltage and then it goes to a maximum of it goes to 1 over here. So the baud here is, so there are two signal changes that you are going to have when you are representing a bit here. So the baud here is 2 here, 2 here, because to represent a bit there are two signal changes that you are going to have here. So this 0 is represented with a positive to negative, and 1 is represented from negative to the positive when you go for this Manchester encoding. So this is what we are talking about, 10 base 5 implementation, 10 Mbps, the baseband signaling, and it goes to a maximum of 500 meters. The cable that you are going to make use of here is a thick coaxial cable, which is not flexible to bend here, and here all the nodes will be connected to this single cable that is running over here. So this we call it as a backbone network that you are going to have here, backbone cable that you are going to have, to which all the nodes will be tapped onto. So this is a transceiver which has the capability of receiving and transmitting the data here. So through this you are going to connect all the nodes to the 10 base 5 implementation, and this is 10 base 2 implementation, where you have 10 Mbps and it goes for a maximum of baseband signaling here, and the maximum length that you can have here for the segment is 185 meters. So here you can observe that this coaxial cable which is used is very thin and it is very flexible also, so that you can bend it here. So all these nodes are being connected to this backbone here, making use of a T connectors, or we call it as a BNC connectors. Making use of them, you are going to tap all of these nodes together. here. So this is 10 base 2 implementation. And in 10 base T implementation, you can see that it is making use of a twisted pair here. And that it goes for a star topology. In the previous two cases, it is a bus topology that is being used. But whereas in this case, you are going to make use of a star topology here. So when you go for the star topology, so there will be a centralized hub that you are going to have. So all the nodes will be connected to the centralized hub. And here you can see that you are making use of two pairs of unshielded twisted pairs over here. So when you go for this two pairs of unshielded twisted pairs here, so one pair is used for transmitting the data from the node to the hub, and the other pair is used for transmitting the data from the hub to the node here. So it makes use of two pairs of UTP cables. So on the other one is 10 base F implementation. So this is 10 Mbps, the baseband signaling, and this is the fiber that we have, fiber optic cable that is being used over here. So this also follows the star topology as we said previously. So this is the hub that you are going to have, to which all the nodes are getting connected here. Here also it makes use of two fiber optic cables, one for transmitting the data from the node to the hub and the other for receiving the data from the hub here. So this is 10 base F implementation of the standard Ethernet. So when we look at various Ethernet implementation, standard Ethernet implementation, and compare them. So the medium that you are going to make use of for 10 base 5 is thick coaxial cable, and for 10 base 2 it is thin coaxial cable, and for 10 base T it is two UTPs that you are going to make use of, and for the fiber optic it is two fiber cables that we have used for connecting the node to the hub here. So this is going for a star topology, these two are going for a star topology, and these two are going for bus topology here, and this is the maximum length that is being achieved here. So 10 base 5 can go to a maximum of 500 meters, base 2 is 185 meters, base T is 100 meters, and base F is 2000 meters that you can have here. So the line encoding that is being used in all the standards is the Manchester encoding that you are going to have. So before they have gone for the fast Ethernet and the gigabit Ethernet and all, so in order to achieve better utilization, so what they have done here is, so here when you go for connecting all the nodes here, various nodes here, you can see that there are 12 nodes that have been connected over a single LAN here, and hence the collision domain will be the entire LAN that you are going to have. That is, even if one node transmits and if the other node here wants to transmit, there will be a collision of this. So in order to reduce this collision domain, so we have they have introduced this bridge here, wherein it connects two different LANs over here. So these two are the LANs, or you can segment the LAN into two, making use of a bridge. So this bridge connects the LAN segments together here. So here the collision domain in this, if at all it wants to transmit the data in this, so the collision domain is limited to this here. And in this, the collision domain is only restricted to this. So this is a bridge which connects the LAN segments that you are going to have. So this is what we were talking about, the collision domains. So this is the entire collision domain, and whereas here, when you have divided it into 4 different LAN segments, then the collision domain is limited only to that particular LAN segment here. So that is the bridge that you are going to have. So maybe 2 LAN segments can be connected with different bridges here. So here only one bridge is being used. Maybe you can have another bridge also to get connected here. If that is the case, there may be some sort of looping that can happen over here. So in that case, you need to make use of some sort of spanning tree over here. You need to go for a spanning tree here, wherein to reach from one segment to another segment, you should use only one path from a particular bridge. If more than one bridges connect the LAN segments, so in that case, you should have only one way of transmitting the data from one segment to another segment. Otherwise, there will be some sort of looping that can happen here. The other type of switched Ethernet is the switched Ethernet that we have. So these are all the various LAN segments that we have. All of them are being connected by making use of a switch. So this is full duplex switched Ethernet, wherein it can transmit and receive the data simultaneously. The nodes can transmit and receive the data simultaneously. So these are the various, this is the enhancements that have been done to the standard Ethernet. And when we have looked into evolution of the Ethernet, we have seen that after the standard Ethernet, the data rates are being increased by going for this fast Ethernet implementation. There are three common fast Ethernet implementations that we have here. 100 base TX, 100 base FX, and 100 base T4. So this 100 indicates that the maximum data rate that we can achieve making use of this is 100 Mbps. It is a baseband signaling that is being used, and this TX indicates that it is a twisted pair that you are going to make use of. Here it makes use of 2 wires of category 5 UTP here. And then this is 100 base FX, where you are going to have the fiber being used. There are a pair of fibers, one for transmission and one for receiving the data that is being used over here. And 100 base T4. So this is going for category 3 UTP here, and this is making use of 4 wires here, 2 for transmission and 2 for receiving the data. So category 5 and category 3 UTPs are being used here. So when you go for category 5, the number of twists that you are going to have in the cable, when you look at the twisted pair, the number of twists that you are going to have, if it is more, we said that noise that gets added is reduced. So in category 5, we have more number of twists here, and in category 3, you have less number of twists. So this offers us a better signal to noise ratio than that of this category 3. So that is about the fast Ethernet implementation. And then moving on to the gigabit Ethernet. So this offers us to a maximum of 1 Gbps. That is the maximum data rate. Makes use of the baseband signaling again. And this SX is the short wave fiber that is being used, and LX indicates this is the long wave fiber that is being used here, and this CX indicates that it is a twisted pair that you are going to make use of. So two copper wires, that is shielded twisted pairs, are being used. In the previous cases, they were making use of unshielded twisted pairs. And the 10 base T is 4 wire UTP that you are going to make use of in implementing this. And the other one is a 10 gigabit Ethernet, which offers us 10 Gbps. So these are the various standard, various evolutions of Ethernet that we have here. So that is about the basics regarding the LAN, Ethernet rather. So the Ethernet frame which you have, I'll just give a gist of this. The Ethernet frame that you have is having 7 fields over here. The first 2 fields are being added at the physical layer. The next field is the destination address, which determines what is the destination address of this particular frame and what is the origin, where this particular frame has originated, that is given in the source address. And the next field indicates the length of the data that is being transmitted, followed by the data that is coming from the upper layer. And then there will be some sort of padding that has to be done here, as there is a minimum size frame that you need to have here, and there is a maximum restriction on the size of the frame. These are the maximum payloads, and this is the minimum payload that you can have over the frame. And at the end, you have a trailer which contains 4 bytes of cyclic redundancy code. So that is the format of the frame. And then we have looked at the categories of Ethernet. And so the evolution of Ethernet, and then we have looked into various categories of standard Ethernet here. So that is the gist of this Ethernet. So now we'll look into what are the protocols that you are going to make use of at the MAC layer. So when you go for this MAC layer protocols, so at the MAC layer protocol, we said that the MAC layer is responsible to resolve the access to the shared link. So when more than one node is connected to the same shared link, then you need to resolve the conflicts that arises due to transmission of the data by two nodes simultaneously. If that happens, then there will be a collision. So you need to control the access to this channel, and that can be done by making use of a protocol at the MAC layer here. So what are the various protocols that we have here? So we can categorize these multiple access protocols into three categories. One is the random access protocol, and the other is a controlled access protocols, and the other one is a channelization protocols. So when you go for this random access protocols, so we call them as a contention methods also, where all the stations are treated equally and there is no station superior to the other station. So no station is superior to the other station in this, and there won't be any control of a station over the other stations here when you go for the random access protocols. And when you go for the controlled access protocols, in this controlled access protocols, the stations have to consult the other stations in order to find out which station has to is given the right to send here. So without the consultation from the other, without getting the acceptance from the other stations, a station should not transmit the data. So a station cannot send the data unless it is authorized by all the other stations here. So under this, we have three protocols. Under the controlled access protocols, we have three protocols: a reservation protocol, polling, and then token passing. So when you go for this reservation protocol, so before the stations actually transmit the data, every station will be given a chance to specify. So first you will be first all the stations has to reserve. If at all they have the data to be transmitted, then they should reserve their slot here. So first the slot starts, the reservation slots start here. So first, if you have n number of stations, first it goes to the first station and checks whether it has any data to be transmitted. If so, the corresponding bit in the bit frame that is being set over there. So then it goes to the next one. So every station sets its corresponding bits to indicate whether it has the data to be transmitted or not. Then the actual data transmission takes place. If the first station has reserved, then the first station can start in the start transmitting the data. And if the other station if the next station do not have the data, it has indicated it as 0. So it will not be transmitting any data. So like this, all the stations have to reserve, and then they will be transmitting the data in turn here, and that is reservation protocol. The other protocol is a polling. So there will be a centralized node here, and this centralized node, it sends a poll signal to every station here. So it sends a poll signal to the first station. Do you have any data to be transmitted? If so, then it sends yes. Then the channel will be allocated for that particular station. In this way, the polling goes on by the centralized node here. And the other one is token passing. So when all the nodes will be, you're going to visualize them in the form of a token ring. So first the node starts here. So if it has the data, it holds the token and then transmits the data. After completion of the data transmission, the token will be passed down to its successor here. So this successor, if it has the data, it transmits. Otherwise, it just forwards this token to the next node. So a station can transmit the data only after acquiring the token in case of this token passing. So all these are the controlled access protocols here, because there is a control of one station over by one station over the other stations over here in a controlled access protocol. The other protocol is the channelization protocols. Here in this channelization protocols, the entire bandwidth that is available by a link is shared here among the stations. When you go for this FDMA, frequency division multiple access, when you go for this FDMA, the entire channel is divided into number of bands here, frequency bands, and every station will be given with certain frequency band, and they'll be transmitting the data in those frequency bands. So from one band to another band, there will be a guard band so that one station may not interfere with the other station here in case of FDMA. And in case of TDMA, the entire channel, the entire frequency will be allotted to every station here, but on a time slot basis. So you are going to divide the time into number of slots here. If at all a station has the data during its slot, only then it can transmit the data. So if you have n stations, so the slots are divided into n. So the first slot will be allocated for the first station to transmit. If it has the data, it transmits. Otherwise, it just keeps quiet for that particular duration. And the next station can transmit only during its slot here. So that is TDMA, time division multiplexing that you are going to have. The other one is CDMA, code division multiple access. So when you go for this CDMA, it has the features of both this FDMA and the TDMA, where the channel can be utilized by all the stations simultaneously, as in the case of FDMA, and at the same time, the entire channel can be utilized by all the stations, as in case of a CDMA. So when you go for this CDMA, it will be based on the codes that you are going to have the communication. So the communication will be done by making use of different codes that are being allocated for various stations here. So these are the other channel allocation techniques, but we'll be focusing mostly on this random access protocols. Why? Because the Ethernet, the standard Ethernet that we have, is following this particular protocol of CSMA CD protocol here. So we'll look at these random access protocols here. So the first, when you go for this random access protocols, as we mentioned, so this is in the random access or the contention methods that we call it as. So here, no station is superior to other station. As we said, that is, no station will be having control over the other station, and no station will be permitting the other station or do not permit the other station to transmit the data here. So at any instance of time, a station, when it has the data to be transmitted, it can follow certain rules here. So we are going to define a set of rules, that is what we call it as protocols, to make a decision whether a particular station can transmit the data or not. So there are 4 protocols that are being given under this random access protocols. The first protocol is the Aloha protocol, which is the basic protocol that we have, and which is a simple protocol. So based on the improvements to this Aloha protocol, only the other protocols like the CSMA, carrier sense multiple access, and the extensions to this are with collision detection and with collision avoidance. So these protocols have originated from this Aloha protocol, which is a very simple protocol, and that is the first protocol that has been introduced. And it is very interesting to learn this Aloha protocol. Is really a very simple protocol that we have here. So when you go for this Aloha protocol, so this is the common channel that is being shared by all the stations. Here, even though it is shown separately, this is a common channel which is shared by all the stations here. So here we have taken an example of 4 stations here, and this is the common channel here. So whenever a station has the data, it does not bother about the other stations in the pure Aloha protocol. So whenever it has the data, irrespective of the time, if it has the data, it just transmits the data onto the channel. It just puts the data onto the channel here. So even the other station, if it has the data to be transmitted, it just puts on the data onto the channel here. So here you can see that at this particular time, the station 1 has transmitted a frame, and station 2 also has transmitted a frame, and station 3 also has transmitted a frame. Even 4 also has transmitted a frame. So there is a collision over here. All of these frames have been put onto a common channel, and hence there is a collision. At this instance of time, you can see that station 2's frame and station 4's frame are colliding. Hence, when every station is transmitting 2 packets each, there are 8 frames that are being transmitted over here. Out of this 8 frames, only 2 frames get succeeded to to the destination. All the other frames are getting collided over here. So in a pure Aloha protocol, irrespective of the time, if a station has the data, it just places it onto the data, and hence the collision can be done even if the last bit of this frame collides with the first bit of this particular frame. Even then there will be a collision here. So the maximum vulnerable period here is 2 times the frame transmission time. So this is one frame transmission time, this is another frame transmission time. During this entire 2 times the frame transmission time, if at all the other station transmits the data, then there will be a collision here. So the vulnerable time here is 2 times the frame transmission time here. So what is the protocol that you are going to use over here? So we'll just put it in the form of a flow graph here. So first we'll send the packet here. So how long, if there is a collision, then the packet has to be retransmitted. How do the sender know whether the packet has reached to the destination or not? So Aloha, it depends on the acknowledgement that you are going to get from the receiver. So when a frame is transmitted, the sender starts a timer which is equal to the round trip transit time. That is, the packet has to reach to the destination and then the acknowledgement has to come back here. So this is the round trip transit time. So it sets this particular timer at the sender with 2 times the frame transmission time. So when the data is transmitted, so first when the frame is getting transmitted, it starts a timer. So if the frame reaches to the other end, then the acknowledgement will be sent over here. So if it reaches within this timeout interval, then the frame has reached to the destination here. That will be getting confirmed by the station. And then it transmits the next frame. If it does not get the acknowledgement within the timeout interval, the timer times out, and then the station will be retransmitting the frame. So if after the retransmission also, if there is a collision, because the other stations also can get a collision, may not be getting the acknowledgement, and hence they may also retransmit. Again, there may be some sort of collision that may occur here, and hence it has to retransmit the frame. How many times a station has to retransmit the frame? It cannot do it infinite time here. So there should be a maximum limit on the number of attempts that a station makes to transmit a frame. So that is normally 15 that is being sent. So 16 times it can go for here. So when a station has a frame to send, so it starts a time. It starts this variable here, which is equal to k. This is the number of times that you are going to retransmit the frame if at all the collision is there and you are not getting back the acknowledgement. So k is set to a value of 0 here. So first, you are not going to wait for the other stations. As soon as you have a frame, start sending the frame. Then, so the timeout interval, you are going to have a timer that is started here, which is equal to the round trip transit time, which is what you are going to consider it as a 2 times the propagation time here. Propagation time is the time that it takes for the packet to go from the source to the destination, and it has to return back. So it is set to 2 times the propagation time. So that is the waiting time. So the timer will be started at the sender with this particular time, and now it waits for the acknowledgement. If the acknowledgement comes within this timeout interval, then the packet has reached to the destination. So it's a success. If not, maybe because of the collision, the packet has not reached to the destination. In that case, you need to increment the value of k. This timer times out, and then you have to go for the next attempt. So increment the value of k over here. So these are the number of attempts that you are going to have here. So if this is less than 15, only then you are going to continue. Otherwise, you will be simply aborting this. So if it is less than this k maximum, then you have to retransmit. So if the two stations have detected that there is has not received the acknowledgement, and they may simultaneously transmit the data, again there will be a collision. In that case, so in order to give different probabilities for the stations to transmit, you are going to make use of a random number over here. So you are going to choose a random number which lies between 0 and 2 to the power of k minus 1. So for the first time, the k value is 0. So it can take the value of either 0 or 1. When the value, when the for the first after the first attempt is made, if it does not succeed, then the k value is incremented by 1. Now k value becomes 1. So it can take a value of 0 to 2 to the power of k is 1, 2 to the power of k minus 1. So it can take a value of 0 and 1 here for the first time. So now you need to wait for a random amount of time here. So picking up from any of these random variables, you will be waiting for this, so that no two stations will be making use of the same random variable. The probability has come down over here. For the first, after the first collision is there, then the probability simultaneously both the stations will not start. One can start with a probability of 0 and one with a random value of 0, and the other can start with a random value of 1 here. So the probability now has been reduced to 1 by 2 here. So the waiting time will be depending on the value of r that you are going to choose here. So once it is chosen, it waits for that amount of time and then transmits the data. If it chooses a value of 0, immediately it starts transmitting the data. If it chooses a value of 1, then it waits for some time to transmit the data. So how long it has to wait, that can be dependent on either the propagation time or the frame transmission time. So every station, once a collision is detected, it chooses a random value ranging from 0 to 2 to the power of k minus 1. Even if in the second attempt also, if it fails, the value of k gets incremented to 2, and then it can take the value from 0 to 3 here. So that the probability of collision of choosing the same value is getting reduced over here. So this is the waiting time that you are going to have. This is what we call it as an exponential back-off algorithm that is being used here. So this is increment. This is repeated for 15 times. If it does not succeed within this maximum number of attempts, then you are going to abort this data transmission here. So what is the maximum throughput? What is the throughput of this pure Aloha protocol? So the throughput, you are going to represent it in terms of S, which is equal to 2 times G, S is equal to G into 2 to the power of e to the power of minus 2G, where G is the average number of frames that are generated by the system during one frame transmission time. So how long it takes for a frame to be placed onto this channel, that is a frame transmission time that we have. How many frames a station can generate during this interval of time, that is what is G here. So S is equal to G into e to the power of minus 2G. So this gives a maximum throughput when the value of G is equal to 1 by 2. And that maximum throughput is 0.184. It implies that 18.4% of the frames can reach to the destination making use of this pure Aloha. So out of 100 frames, only 18.4 frames will be reaching to the destination making use of this pure Aloha. So the performance is very poor in case of pure Aloha protocol. So this has happened because there is no restriction on the stations to transmit a frame. Here, at any instance of time, they can transmit the frame. So they have introduced a restriction on the time at which the frame has to be transmitted, and they made some improvement to the pure Aloha protocol, which resulted in a slotted Aloha protocol. So when you go for this slotted Aloha protocol, all the stations has to transmit the data only at the beginning of a slot. So the time is divided into number of slots here. All the stations, even though if it has the data, it will not be able to transmit it at the middle of the slot. It has to wait until the slot begins here, so that the vulnerable time here is getting reduced by half here. So only one frame transmission time is the vulnerable period over here. So only during this time there can be collisions. So this is the vulnerable time that you have here, which is equal to the frame transmission time that you are going to have here. So at this point, if the frame starts, then before this, if you have the frame, if a station have the frame to start, it can't start at this point. It has to start only at the beginning of the slot. And hence, in this period, there won't be any sort of collision once a station starts transmitting the data. So at this time, two stations may transmit the data simultaneously, and hence there will be a collision. So the vulnerable time here is only the frame transmission time. So during this time only there can be collisions here. So the throughput of the slotted aloha here, you will be getting at a value of G is equal to, maximum throughput you will be getting at a value of G is equal to 1, and that is equal to 0.368, where it implies that 36.8 frames out of the 100 frames that you have transmitted reaches to the destination. So this is slotted aloha protocol. So we'll move on to the other protocol, which is the carrier sense multiple access protocol. So here, when we look at either the pure aloha or the slotted aloha protocol, the maximum throughput that we can achieve is less than half of the maximum bandwidth that we have here. So how to improve this? So this has happened because the station, when it is transmitting the data, it is not looking at the other stations. If the other stations are transmitting the data, if this station can hold for some time, then there won't be any sort of collisions. That reduces the number of collisions here. So before you transmit the data, if a station can sense the data and then transmit the data, that is, sense before you transmit the data, then the number of collisions can be reduced over here. So that is what we make use of in this CSMA protocol, carrier sense multiple access. So carrier sense. So carrier in the sense, first before the data has to be, before a station wants to transmit the data, it looks at the channel. Is there anyone who is making use of this channel? And that can be noted by looking at whether any data is being transmitted over the channel or not. If the channel is idle, then it can start transmitting the data. So this is the principle behind the CSMA. So listen before you talk. So then there won't be any sort of collisions here. So when you go for this CSMA protocol, do you feel that there won't be any sort of collisions if you are going to sense the channel and then transmit it? No, there will be collisions even in the CSMA protocol also. Why? Because of the propagation time that elapses here for a frame to get transmitted to the other end. In this example, you can say this is the space-time diagram that we have here. So this is the timeline that you have, how the data is getting transmitted by various nodes that is represented in the space-time diagram here. So at time t1, station B has sensed the channel and it has found that the channel is idle because it has not received any data from the other nodes here. It has not sensed any bit over here at this instant. So it starts transmitting the data here. So to reach to this end, it takes certain time. So this is the time it takes for the packet to reach to the destination here, to reach to the other node. So during this interval, if at all the other station senses the channel, as it does not listen to this data that is being put by this B onto the channel, it senses that the channel is idle and hence it also can transmit the data because the first bit here has not reached to the C. So when it senses the channel, it finds that there is no data that is available over the channel and hence C can start transmitting the data. At this instant, you can see that there is a collision. So the first bit of this B collides with the first bit of the C. First bit of the packet that is transmitted by C, and then there is a collision. This has happened because of the propagation time. So what is the vulnerable period here, vulnerable time here, the time at which the collision can happen? So this is the propagation time. So you have to consider the maximum propagation time here. That is This is the first node and this is the last node. How much time it elapses for a packet to be transmitted from this node to the other node. The first bit has to reach to this node here. So the first bit is transmitted at this particular time and it has reached to this destination at this time. So this time that elapses here is what we call it as a propagation time. And that is the time during which the collision can happen. Why? Because when a station senses this, as this particular first bit is not reached to this, there is a chance that this detects that the channel is idle and hence it can start transmitting the packet. So this is the vulnerable period here. So this is the transmission time and this is the propagation time that we have. So this is carrier sense multiple access protocol. So here, when you are detecting the channel, when you have detected that a channel is busy. So this is a case when you have not detected, when you have detected the channel is idle, it starts transmitting. And at this instance of time, so at this instance of time, say, at this instance, C has sensed the channel. It finds that the channel is busy. Why? Because the first bit has reached to C and then it has sensed that the channel is busy over here. So when it senses the channel busy, what this particular station has to do? What should the station do if the channel is busy? Or if it finds that the channel is idle, what it has to do? So based on that, we have different methods that can be applied over here. So there are three persistent methods that have been introduced here in order to check what has to be done if at all it senses the channel as busy or if it senses the channel as idle. So there are three persistent methods that we have. One is a one persistent, the other one is non-persistent, and the other one is a p-persistent method that we have. So when you go for one persistent method, so first every station senses the channel. If the channel is busy, then it continuously senses the channel until the channel becomes idle. When it finds that the channel is idle, then it immediately starts transmitting the data here. So this is busy waiting here that happens in a one persistent CSMA. So it will be eager to transmit the data. So it will be continuously sensing the channel, and then if once it finds the channel is idle, then it immediately starts the transmission of the packet. So what happens if two stations found that the channel is busy and they'll be continuously sensing the channel, and when they find that the channel is idle, both of them simultaneously starts transmitting the data, and hence there will be a collision here. So one persistent CSMA results in more number of collisions here. So this is called one persistent. Why? Because with a probability of 1, the channel, the station sends the data onto the channel here. And the other one is non-persistent CSMA. And when you go for this non-persistent CSMA, in case of a non-persistent CSMA, first the channel will be sensed. If the channel is idle, it immediately makes use of the channel. If the channel is found to be busy, rather than busy waiting, checking for the channel, it just waits for a random amount of time and then it starts sensing the channel here. So this random amount of waiting can be varied from one station to another station here. And there again, you can follow some sort of exponential backoff also. So that no two stations will be making use of the same random amount of wait time here. So that the chances of collision can reduce here when you go for non-persistent CSMA. So with a probability of 0, you are going to transmit the data over here onto the channel, and hence this is non-persistent CSMA. So the other one, when you go for this non-persistent CSMA, there will be less number of collisions because the stations are going to wait for a random amount of time here when you go for this non-persistent CSMA. But the channel efficiency degrades when you go for non-persistent CSMA. Why? Because two stations may be waiting for a random amount of time and they're not going to transmit even if the channel is idle. here. So because they'll be waiting for some time to elapse, during that time the channel may be idle, and hence no station will be transmitting the data during that time, and hence the efficiency of the channel may be reduced when you go for non-persistent CSMA. And that is why they have introduced this P-persistent CSMA. In order to effectively utilize the channel, at the same time, you need to reduce the number of collisions here. So what happens in this P-persistent CSMA is you're going to divide the time into number of slots over here. That slot should be greater than the frame transmission time here. So first it senses the channel. If the channel is idle, it immediately does not start transmitting the data. Rather, with a probability of P, it transmits the data. If the P that you have selected is less, so it starts transmitting the data with a probability of P. So with a probability of P 1 minus P, it waits for a slot. And then it senses the channel before it could transmit the data. If it is the channel is idle, then again with a probability of P, it is going to transmit. If the channel is busy, then again it goes for a back off process as though there is a collision that has occurred, and then again it starts sensing the channel here. So this is P-persistent CSMA, which reduces the collisions and which reduces the number of collisions that may happen, and also at the same time the efficiency of the channel also gets increased over here. So this is the 3 persistent methods that we make use of in the CSMA protocol. So now we'll look at CSMA CD protocol, carrier sense multiple access with collision detection. So when you go for the CSMA, there is a collision over here. What action has to be taken when there is a collision? That is not defined in CSMA protocol, and hence the CSMA protocol has been modified to go for CSMA CD protocol with collision detection, and the other protocol is with collision avoidance. Both the protocols are being designed simultaneously as an improvement to this CSMA. So when you go for the CSMA CD, this is what we make use of in the wired network, and CSMA CA is the protocol which is used when you go for a wireless network over here. So when you go for CSMA CD, once the collision is detected, then the stations have to take the action. So that the action that they take is, so once they detect that there is a collision, it immediately stops transmitting for the frame. So it has to say, for example, this has 1000 bytes to be transmitted. After 100 bytes of transmission, it has detected that there is a collision. Then the remaining 900 bytes will not be transmitted by this A here. So after the collision is detected, then the CSMA protocol will stop transmitting. The station will stop transmitting the data over here. So this is the action that is being taken, and that is a new protocol known as CSMA CD protocol, and this is the protocol that is used in the Ethernet MAC layer here. So as soon as the collision is detected here at C, it has immediately stopped transmitting. So only this amount of data from C is being transmitted over here. So at T2, C has started transmitting that packet, and at T3, it has detected that there is a collision. How do you detect that there is a collision? The collision will be detected by the stations seeing at the amplitude of the signal. So when two signals collide, there will be a raise in the amplitude of that signal, and based on this amplitude of the signal, you are going to detect that there is a collision here. So at T4, a station A has detected that there is a collision, and hence it immediately aborts the data transmission. So this is CSMA CD protocol, which is used in the wired LANs. So when you go for this frame format, we have seen that there is a limit on the size of the minimum size of the frame that we have, and we said that it is around 64 bytes. That is the minimum size of the frame. That is, the payload should be not less than not less than 48 bytes. That is what we have said in the when we have looked at the frame format. So why is it that there is a restriction on the size of the frame? There we mentioned that it is because the CSMS CD protocol is being used in the Ethernet. This restriction has come here. So the a network making use of CSMS CD protocol has a bandwidth of 10 Mbps. This is the standard Ethernet, which has a maximum data rate of 10 Mbps. That is the bandwidth that we have here. And if the maximum frame propagation time is 25.6 microseconds, this is the propagation time here. So what is the minimum size of the frame? So here we'll talk about this jamming signal later. First, we'll just consider that the maximum propagation time is 25.6 microseconds. And what is the minimum size of the frame? So this is the standard maximum propagation time for a standard Ethernet that we have here. So the maximum data rate is 10 Mbps and the maximum propagation time over this link is 25.6 microseconds. Now, what is the minimum size of the frame that we have? So the restriction is that, so here when the station is transmitting your data, when can it detect that there is a collision? It need to listen to this. So the data has to go, and then if there is a collision, the signal has to be received by this. So this is the frame 2 times the propagation time that the station has to listen to this channel so that it can detect that there is a collision. So the frame transmission time that you have should be 2 times, at least 2 times the propagation time. Why? Because when a station in CSMS CD protocol, when a station starts transmitting the packet, when it completely puts the packet onto the channel, it simply ignores that. It won't maintain a copy of that. And hence, if there is a collision after the frame is being transmitted, it will not be listening to the channel anymore here. And hence, until before the last bit of the frame is placed onto the channel, it has to detect the collision here. And hence, the frame transmission time should be at least 2 times the maximum propagation time, so that if the collision happens at the farther end, then it has to detect the collision. So it takes the propagation time to move from this end to the other end, and from there it has to come back. So the frame transmission time should be at least 2 times the maximum propagation time. And that has placed the restriction on the size of the frame that you are going to transmit here. So that is what you will be seeing over here. So the maximum bandwidth that we have in a standard Ethernet is 10 Mbps, and this is the maximum propagation time. So there we know that the distance that you are going to have is around 185 meters when you go for 10 base 2. So based on that, you are going to derive this maximum propagation time. So this is the maximum propagation time. So now what is the minimum size of the frame? So the restriction is that the frame transmission time should be at least 2 times the maximum propagation time. So the TFR should be equal to 2 into frame propagation time. So what is the propagation time here? Maximum propagation time is 25.6 microseconds. So TFR is equal to 2 into TP, that is 51.2 microseconds. That is, this frame should take 51.2 microseconds to be placed onto the channel. So it takes 51.2 microseconds at the max to detect that there is a collision here. So the minimum size of the frame should be, so this is the bandwidth into the frame transmission time. So this gives the minimum number of bits that we should have in the frame transmission time, because the frame transmission time is equal to size of the frame divided by the bandwidth. So length is equal to frame bandwidth into the frame transmission time. So it goes to 512 bits, which is nothing but 64 bytes, and that is the minimum length of the frame that you should have in a standard Ethernet. So that is what is the restriction that we have mentioned when we have specified about the frame length over there in the when we have looked at 802.3 frame format. So this is the flow diagram for CSMA CD protocol. So when we look at the CSMA CD protocol, it is an extension to the CSMA protocol here. So here, similar to that of Aloha protocol, you need to have maximum number of attempts over here. For that, we'll be keeping track of by making use of a variable here. So the maximum number of attempts, generally Kmax is set to 15 over here. So initialize the value of k equal to 0, and you can make use of any one of these persistent methods to transmit the data here. Any one of these non-persistent, p-persistent, one-persistent methods to transmit the data. Here, when you are transmitting the data, here as in the previous cases, in case of CSMA or in the Aloha, the entire frame is transmitted and then we are going to listen to the acknowledgement. But here in this particular case, CSMA CD protocol, as soon as you place the data, the station has to listen to the channel also here. That has to happen simultaneously. So this is done simultaneously. So simultaneously, it has to transmit the data as well as it has to listen to the data. So either of these two can happen. Whether the transmission has been done successfully, that is, you have not heard any sort of collision that is being detected over here, then we say that the transmission has been done successfully. If not, there is a collision that has been detected here. So simultaneously, you need to transmit as well as you need to receive the data. It is in a continuous loop that you are going to have. So once you detect that the data is transmitted successfully for this period of time, then you won't see that there is a collision. If at all, before this time elapses, if at all, the entire frame before it is put onto the channel, if you have received a signal from the other end, then it indicates that there is a collision. So if there is a collision, then what has to be done? If there is no collision, the transmission is done successfully. If there is a collision, then what has to be done? So here, before it goes for a exponential back-off algorithm, what this station will do is when a station detects that there is a collision, then it immediately sends a jamming signal to all the other nodes here, so that all the other nodes which has not learned so far about the collision will be alerted regarding the collision. So that is the purpose of the jamming signal. So in the round trip that you have, when the data is propagated back again to the station, so this jamming signal time also gets added to this. So for the total round trip transit time, this also gets added here. The jamming signal time also gets added here. So then you're going to increment the value of k so that you will be going for the next attempt here. So when the value of k is greater than k maximum, then you're going to abort. That is maximum number of attempts that you are going to make. If it is greater than the 16, then you are going to abort this. Otherwise, what you have to do, you have to choose any random value lying between 0 to 2 to the power of k minus 1. Now the k value is getting incremented. For the initial time, it is 0, and for the next time, it has been incremented, so that the values can be ranging from 0 to 1 for the next attempt, and then the station chooses any one of these k values here, r values over here, and they will be waiting for a random amount of time here. And then they again start with the p-persistent method until they get succeeded or until the maximum number of attempts are being made to abort the data here. So simultaneously, a station has to send the data as well as it has to sense the channel, receive the data from the channel. So this is CSMA CD protocol, which is used in the Ethernet, standard Ethernet here. When we look at the efficiency of CSMA CD protocol, here we said that the transmission delay has to be greater than or equal to 2 times the propagation delay. So that is the length of the frame that you should have should be greater than or equal to 2 times the bandwidth. So L by B is the transmission time. So B if you take over here, so then L is greater than or equal to 2 times the bandwidth into the propagation delay. The propagation delay is the distance divided by the velocity or the speed of the transmission here. So the efficiency, you will be getting it as total transmission time divided by the total time here that takes here. So if you are going to have the collisions, then you are going to wait for this an amount of time. Then again you need to retransmit here. So this is the efficiency considering the number of collisions here. If C is the number of collisions, that is what. In the average, if we look at the average, if you look at the efficiency, this will be equal to 1 by 1 plus 6.44A, where A is equal to the propagation time divided by the transmission time. So based on this, I have a question over here based on this. So the efficiency of the Ethernet. What happens to the efficiency of the Ethernet in relationship with propagation delay and the transmission delay? So the efficiency of the Ethernet increases with the propagation delay and transmission delay. When the propagation delay as well as the transmission delay are low, then the efficiency of the Ethernet increases? No. When we look at this efficiency is equal to 1 by 1 plus A, where A is TP by TT. So it is the denominator here. So it will be TT by TP. So efficiency is directly proportional to TT and is inversely proportional to TP here. And hence the answer is the efficiency increases when the propagation delay is low and the transmission delay is high. Why? Because it is T by TP that you are going to have here. So if TT is high, then the efficiency also gets increased. If propagation delay is low, then the efficiency increases. So the efficiency of the Ethernet increases with the propagation when the propagation delay is low and the transmission delay is high. So we'll stop here for today, and in the next class we'll look at some of the problems that have been given in the previous GATE examinations related to this CSMS-CD protocol, and later we'll move on to the next topic that is wireless LANs. So, thank you.